Hi, good evening, everybody. Welcome to session 2 for Vibrational Dynamics. This is on the first part of chapter 2, which hopefully you've all done the pre-study work for this session. Thanks for joining us at this hour. I know it's not ideal, but it's not ideal for me either. But, there we go. Right, so we're going to start off, like all the sessions. We're going to start off with a quiz, with a poll. If you all want to get out a device, or a mobile phone, tablet, whatever, go to www.menti.com and enter this code 8224928, and then there's going to be some questions. Yes, okay, looks like you can see that. Okay, so did you cover all the material in sections 2.2 to 2.4? Looking good so far. There are 46 of you in the room, so I'm expecting some results. The code is at the top of that screen, 8224928. Like I said, 47 of you in the room, 36 have responded so far, and it's looking good. Okay. Any more for any? Okay, well, let's move forward. Okay, well, that's great. I mean, I'm pleased that most of you seem to have looked at all the content, and 10 of you some of it. And I hope that you found the sort of the Jewish test relatively straightforward, following having covered the content. Okay, did you watch the videos just out of interest? And which was that the main way that you did it, or did you read the notes, or did you do a bit of both? Theo's got a very good strategy there. With the notes and added info from the videos, that's a great way of doing it. Engaging with the video and the notes at the same time. Okay, 40, that's great. That's really good. I'm pleased that people are using them. And I'm pleased that nobody's ticked the no, I didn't have the time button. You're all finding the time, which is great. Well done. Okay. And lastly, for this for the sort of survey, did you feel apprehensive about the delivery method? Okay. Let's see. I mean, I guess for this year, it's not that unusual because a lot of modules are being, in the sense, pre-recorded lectures supported by small group, face-to-face, and in class and lectorials. So that's a nice response. Excellent. Okay. Any more? 36, 39. Great. Okay. Let's move forward. Thank you. Right. Now we've got now we're going to move on to a quiz. Okay. On the content, just to gauge your level of understanding and my level of understanding. So have a go at this question. With undriven systems, how do you determine amplitude and phase angle? And at the moment, I shall hide the answers. I'll give you I guess, about 30 seconds, and then we'll so far we've got 2 answers. Okay. Use the parameters of the system, use initial conditions, use details of the applied force, or do you plot the solutions and read the value from the graph? "29 responses, any more? 30? Okay, that's 30 seconds. Any more? Last call. Last call. 37. Let's get to 40. 38. Any more? 2 more? Guess if you don't know. Okay. Right. Okay. Well, that's good. That is indeed the correct answer. Use initial conditions. Okay. Oops. There we are. Use initial conditions. That's the correct answer. Okay. I sort of gave you a hint there because I was showing the correct answer. Okay. So yes, with undriven systems, the amplitude and phase angle are determined by your initial conditions. That's the only way you can work that out. The amplitude being the A value and phase angle being there's angle, which I think for undriven systems is either alpha or phi. Okay, so that's how you determine the amplitude and phase angle. For driven systems, it's not the case. Okay, so a system is driven by an oscillatory force. What is the steady state oscillation frequency? Okay, so again, enter what you think, whether that's omega naught, omega n, omega d, or just omega without any suffix. Okay, another 30 seconds from now. $37. Any more? Any more? Last 5 seconds. I'll come back in a minute. Right. Okay. So the answer is indeed omega. Well done, everybody. Okay. Omega is the correct answer. Omega naught is natural frequency. Omega n, sometimes that's been referred to as natural frequency, but I shall be talking about that in chapter 4 with a slightly different reason. Omega d is known as the damped natural frequency, and omega without any suffix is the driving frequency of the system. So that's the system at that is the frequency at which you're driving the system at of your choice. Okay, irrespective of what the system wants to oscillate at, you to get to decide what omega is. Okay, and eventually, after initial conditions are sort of, or after the initial situations has died away, that is the frequency at which the system will oscillate at in the steady state. Okay, we'll talk about what happens in between when we get to chapter 3. But like I said, if you're driving a system, the steady state oscillation frequency, the steady state meaning as time goes off to infinity, what is the frequency? It'll be the frequency at which you're driving it. Okay, so a mass spring system is subject to free oscillation. The equation for displacement is A, B, C, or D. Okay, a mass spring system is subject to free oscillation. The equation for displacement is A, B, C, or D. Okay, another 30 seconds. $27. A mass spring system subject to free oscillation. Any more? 36, 37. Okay, let's go for it. Okay, we have 22 choosing option B, and indeed 22 of you correct. Okay, that is the free oscillation. That's the equation. Okay, we've now got another question. A mass spring system is now subject to forced oscillation. What's its equation for displacement? A, B, C, or D? Again, 30 seconds. Any more? 35 seconds to go. Any more answers? Okay. Okay, last call. Right, so A, B, C, or D? Okay, people chose D. Let's see what the image was. Okay, so for a driven system, you're correct to get the omega t minus delta, but I guess C or D could be an answer for this question. And if you look at the results, some of you are choosing C or D, because they're very similar in a sense. You've got one with minus delta and one without a minus delta. But the way you work out the amplitude, and in the case of D delta, is very much dependent upon the type of system that you've got. But well done. Anyway, it's not omega. It's not A or B because we're not oscillating at the driving frequency. Are we in the distance? Okay, so next question. Mass spring damper system is subject to free oscillation. The equation for displacement is there's a mass spring damper system. Okay, again, I'll give you 30 seconds. We're getting closer to using the process of elimination here. "15 seconds. I should have countdown music playing, shouldn't I, really? Any more? Okay. So the answer is indeed A. Well done, everybody. Yep. If we show the image, you can see that we've got an omega D up here, which gives you an indication that it's oscillating at a damped natural frequency. And we've got this decaying exponential up here. As t goes off to infinity, this number gets closer and closer to 0. So obviously with a damped system, you start it oscillating, it will start oscillating at a slightly slower frequency than its natural frequency, and it will decay away to 0 over time. So that's quite clear why that's the equation. Okay, and the last one. So if we go to that, let's do that. There we are. Okay, and the last question. Mass spring damper system is subject to force oscillation. Process of elimination. So I'll give you 20 seconds. Okay. Spring damper system subject to force oscillation. What's its equation for displacement? Okay. Any more? Let's go for it. Okay, so hide. Okay. Slightly even distribution. The answer is indeed D. Okay, that's what we use for forced oscillation. So if I click that, you see D. Okay. And if I show you, like I said, A and delta are determined by the conditions of the characteristics of the system specifically. Okay, another couple of questions. Or perhaps this is the last one. I can't remember. A mass spring damper system is subject to forced oscillation. Match up the frequency with the amplitude. So we've got some answers here that are 1A, 2B, 3C. So you need to match them up correctly and so on. So forth. It's not 1A, 2B, 3C, by the way. Okay, so have a go at that. What do you think? When omega approaches 0, what is the amplitude of the system? When omega approaches the natural frequency, what is the amplitude? And when omega approaches infinity, what is the amplitude? Any people gonna have a guess? Looks like nobody's responded so far. I'll give it a little bit longer. If you obviously need to look it up in the notes, perhaps. Okay, coming up to a minute now. Any more? This is a tough one, I guess. Okay, so if we go back, let's see the answers. Okay, well done. Yep, 15 of you got that correct. The answer is indeed B. Okay, if we go back to the image, okay, you can see that a 0 oscillation frequency, so that we're not actually shaking the system. The position of the system, or the amplitude of the system, is simply a static displacement, which is F naught divided by K. If you rearrange this equation, equals A equals F naught divided by K, well, A is a displacement. We know that displacement times by stiffness gives you the force that's being applied, or the force that's being applied is simply the stiffness times the displacement. So 1B goes together, okay? As omega approaches infinity, the faster and faster you shake it, the closer the amplitude is actually going to get to 0. So you've got 3A, okay? And therefore, you can either by process of elimination or just by knowing it. As omega approaches omega naught, so we're approaching the natural frequency of the system, we get depending on the damping, we get an uplift in the level of amplitude. Amplitude can grow, and if you've got a system that's nicely underdamped, your Q value, your quality of oscillation is big, so a large increase in the amplitude. F naught upon K times by this value Q, which is the quality oscillation. Okay, so the learning objectives for chapter 2. Okay, you should be able to, and there's basically chapter 2. We're taking 2 weeks over because it's quite a relatively lengthy chapter. And this week it's these 2 sections. Okay, being familiar with standard alternative forms of the solutions, both free and forced, undamped and damped single degree of freedom system equations, and understanding how these have been determined, and understand how for forced systems amplitude ratio varies with driving frequencies. Okay, that was the last question, essentially, last quiz question. So in terms of activities for this session, very quick overview of undamped oscillation. We'll have a go at in-class questions 2.1 and 2.2. Okay, talk very briefly about damped free oscillation. There's another in-class question which I may just do because of the time, and likewise talk about damped forced oscillation, another in-class question again which I may just do because of the time, and then we've got an example at the end which I will be doing anyway, either which way. We'll see how we get on in terms of time. So the main sort of focus of this chapter, the main takeaway is knowing what these equations are. Okay, so basically being familiar with what I guess being familiar with what they come from, but really what they are and how you apply them. Okay, so we've got 4 sort of situations. We've got damped and free and forced, and that forced is actually known as the steady state. Okay, so as time goes off to infinity, what does the displacement look like? Okay, for the undamped case, obviously you've just got this basically an equation for a sinusoid. It's got a certain amplitude A, a frequency, which is the natural frequency of the system, okay, and a phase angle, phi, and A and phi are both determined from initial conditions. For the undamped system, where you've got a force system, you've got an amplitude that's defined by the system, by the force, and the natural frequency and the mass, sorry, the stiffness and the mass and the driving frequency, and it oscillates at the driving frequency. For the damped system, you've got that Cx dot term in there because it's damped. Pre-oscillation, you've got this decaying exponential built in, and the frequency of oscillation is omega d, damped natural frequency. A and alpha again are determined from initial conditions, and then for the force system, you've got an oscillation frequency of your driving frequency. A and delta are to be determined from characteristics of the system and of the force. And like I said, you can apply some equations to find out what those things are. Okay, so just again briefly, undamped oscillation. You've got a system at the top here where ft is 0, and for the driven one, we've got this ft is not 0. It's some sinusoid, and like I said, you can't adjust the amplitude of that system. And omega, without a subscript, is the driven frequency. So let's have a go at this. So I'm going to give you let's go 5 minutes. Have a go at this problem, okay? Now, again, this is a Mentimeter, so if let me just stop sharing that and oops, go back here and go back to the Mentimeter. Share. Okay, so there's the in-class question. That's all. Let's hide that. Okay, and yeah, so have a go at answering these questions. Okay, 5 of you have already gone for it. That suggests that you've done it beforehand, or you spotted what the solution was. Okay, there we go. Right. Okay, so there we go. Okay, pretty good. That's the correct answer. Okay, now here we go. We're going to try something unusual now to just show you how to do the solution. Yeah, there you can see it. Right. Okay, car of mass 1500 kilograms is designed to have a natural. Yeah, okay, that's fine. Thank you. Yes, you can see it now. I know. I can see that you can see it. Right. So we've got a natural frequency of 1.5 hertz. So the natural frequency in radians per second, which is what we want, is 2 pi times by f naught, which is 2 pi times by 1.5. This comes out to be 9.4248 radians per second. Okay. We know that omega naught, at any single degree of freedom system, the natural frequency, this undamped natural frequency, is root k upon m. And so we know that if we rearrange this equation, we know that k is going to be omega naught squared times by m. We've got 9.4248 squared times by m, which is 1500, and we get 133.240 times 10 to the 3 newtons per meter. Okay, there's the answer. What about 2.2? So this time it's not a free system. It's being an oscillating force. Okay. Again, if you could give your answer in Mentimeter, but the question is a mass spring system within a packaging machine with an effective mass of 2 kilograms and a spring stiffness of 45 newtons per meter is subjected to an oscillating forcing function described by 10 cosine 3t. What is the steady state amplitude of the resulting oscillation? Okay. So again, if you could give your answer using Mentimeter, I shall share the Mentimeter screen. Have a go at answering this question. Okay, let's see how we're getting on. Okay, well, it looks like you mostly got that right. Indeed, the equation you're applying is simply the amplitude equation 2.12. Okay, which you can obviously see on page 19 of your course notes. So I shan't go through the solution since most of you got it right. Be aware of your units for those people that chose millimeters. Okay, and those people that, well, for that person that got chose answer A, you need to make sure you're aware of the frequency that you're applying. I think that's possibly the reason for that. mistake. Okay, so damped oscillation. When you've got damped oscillation, you've got a system here. You pull it back x distance, you let it go, and then it will oscillate. Because there's a damper that's taking energy out of the system, that oscillation will eventually reduce to zero. Okay, and that's accommodated by the decaying exponential part in this equation of motion. Okay, the amplitude and the phase alpha, they depend upon initial conditions. Okay, and the omega d is the damped natural frequency, and it depends upon the damping. The higher the damping that you've got, the lower the damped natural frequency will be, and the bigger difference between that and the natural frequency. In this module, we're only going to be dealing with underdamped systems because that seems to be the most common type of damping that we deal with. So, like I said, so we're not going to wander into the realms of critical damping or over damped systems, mostly underdamped systems. Okay. There is an in-class question, but I'm going to do it. Okay, so that's how you work out the natural frequency. Okay, it's based upon the natural frequency, and from that you subtract the amount of damping. So that's mass-specific damping there, C upon M, which is gamma. And you reduce, like I said, you take that away. So the omega d would always be less than omega naught. So, like I said, in class question 2.3, I shall just do it, I think, because we haven't really got time to focus too much on giving you the opportunity to have a go yourselves. So if I just bring that up now, here it is. Okay, so you can see it, 2.3. Locomotive car of mass 2,000 kilograms, traveling at that's a very light locomotive car, traveling at a velocity of 10 meters per second, is stopped at the end of some tracks by a spring damper system. If the stiffness of the spring is 40 newtons per millimeter and the damping constant is 15 newton seconds per millimeter, find the equation x of t representing the motion of the locomotive when it hits the buffer. And we've broken it up into steps. Okay, so we use equation 2.7. We must find gamma and omega d. Okay, let's find gamma first. Well, gamma is C upon M. Okay, and notice that we've got millimeters in the question. Okay, so that's actually going to be 15 times 10 to the 3 to get it into SI units, divided by the mass, which is 2,000, and so we get a gamma value of 7.5 seconds to the minus 1. Okay, damped natural frequency d. We'll use that equation. The square root of omega naught squared minus gamma squared on 4. Okay. Omega naught squared is simply k upon m minus gamma squared on 4. So we've got k, which is 40 times 10 to the 3 divided by 2 times 10 to the 3 minus 7.5 squared divided by 4. That comes out to be 2.437 radians a second. So here I've actually given you some initial conditions. Okay, so we're going to define them. We're going to work out what A and alpha are. Okay, and what I've actually done for you is I've given you the equation for displacement. So I've taken the equation for the solution. Okay, is that decaying exponential, and then I've differentiated with respect to time. Okay, I notice that we've got to use the chain rule and the product rule, which is why you've got two terms there as opposed to just a single cosine term. Okay, so that's you've got to bear that in mind. But for this example, I've given you the derivative. So that's an equation for velocity. Notice the dot on top of the x term. So if you've got our equation of motion for displacement, x of t, we know it's going to be in this form. Okay, that's what we worked out. And obviously x of naught. Okay, so the initial displacement, we've got a, e to the 0 is 1, so that disappears. And we have cosine. Obviously, omega d 0 is 0, the cosine of alpha. Okay, we know that initial displacement at time equals 0 is 0. And for this, that must mean that cosine of alpha equals 0. Because a equaling 0 doesn't make sense, because that's an amplitude. There will be an amplitude of oscillation. The cosine of alpha must be 0, and therefore alpha must be I divided by 2. Okay. If you think about the curve for cosine, when cosine curve crosses 0, the angle of that is pi divided by 2. Okay. So we've got alpha. Okay. We then need to work out for the velocity when time equals 0. Okay. Again, we've got a. Okay. E to the 0 is 1. Okay. We then we've got what have we got? Of course, minus gamma upon 2 as by cosine of alpha. Okay. Minus omega d as by sine of alpha. Okay. Whoops. Now we know that this value is 0. That's already up here. Okay. Sine of pi by 2 is 1. Okay. So that goes to 1. So we end up with this equals 10. So we have a times by minus omega d equals 10. Therefore, a must be 10 divided by minus omega d. That's 10 divided by minus 2.437. This comes out to be minus 4.1104 meters. And so our equation of motion, we just plug everything back into the equation up the top here, this one here. Minus 4.104 e to the minus 3.75 d cosine of 2.437 t plus pi divided by 2. Okay, there's our equation of motion. So based upon those inputs, we have an output displacement looking like that. Oh, just saying sorry, I'm not quite sure why. Where did gamma over 2 go? Gamma is 7.5 divided by 2, we get 3.75. Is that okay? Multiplied by a 0 term. Gotcha. Sorry, what are you talking about? Yes, yeah, multiplied. Cosine of alpha is 0, so that term disappears completely. Okay. I think I've planned too much for this session. I could go beyond 8 if people are happy for me to do so. Okay, let's have a show of hands. Who wants to go beyond 8 o'clock? Okay. Any more? Okay, we've got 18 people out of 46. Not quite halfway. Why don't I make? I'll cut the difference. I'll go a little bit beyond 8 o'clock, but not too much. How about that? Okay. I shall lower hands if that's okay. I'll go for 10 minutes or something. If that's okay. So if you could lower your hands, that'd be good. I can't do it on maths. That'd be great. Okay. If you've got a genuine question, you can also raise your hand. Okay, so downforce oscillation. Okay, this is where it gets a little bit complicated. Okay, because A and delta are not simple equations. Okay, I went through quite a convoluted solution process to get here, involving complex numbers and complex numbers by complex numbers. Okay, but like I said, the most important thing is not the derivation of this equation, but also is how to work it out. Okay, so here we've got equations for A and delta. Okay, if you did the in-class question for this this part of the chapter, sorry, not the in-class question, the Jewish test, then you would have been familiar with these equations because that's what I asked you to solve. Okay, applying the equations for A and delta to give you the two answers that you needed. Okay, so so omega again is the driven frequency. Omega naught is the natural frequency. We've got F naught, which is the forcing amplitude. Okay, and obviously omega without the suffix is the driven frequency. Okay, so the equation involves gamma, involves M, and involves the natural frequency as well as the driving frequency. And depending on various values, you get a certain amplitude. So the way the sort of the amplitude works in terms of the natural frequency, like I said, the driving frequency. R is the frequency ratio. So when R is 1, the driving frequency and the natural frequency are the same. And 1 for the amplitude ratio is F upon 0. That's just static displacement. So as you can see, as you move increasing frequency, you get a peak depending on your value of damping, and then as you go beyond the natural frequency, that amplitude will eventually go to 0, and you can see that the phase angle, this delta, goes between 0 and pi. That's important to remember, okay, in terms of the angles, because when you do the sums on your calculator, you might get a negative answer, and obviously for that you need to move it to a different domain. So you can see that obviously as we go through, we start out, the system moves in the same direction as the way you're applying the force. At the natural frequency, it's moving 90 degrees out of phase, so it's following the force by 90 degrees. And then as you go beyond into much higher frequencies, the system, although the force is applying, say, to the left, the system is actually responding to the right, because you're 180 degrees out of phase, or pi out of phase. Okay. And then in terms of, like I said, that's the equation. Okay. And it's, like I said, it's important. If the natural frequency is less than the driving frequency, so if you're driving the system faster than the natural frequency, this sum will come out to be negative. Like I said, delta is not negative. It can't be negative. It's between 0 and pi. And so what you need to do is you need to take your negative answer and add pi to it. Okay, so you take your negative answer, you add pi to the character, and that will give you the correct phase of that force. So there's question 2.4, and what I'll do is I shall do this question, and now I think we'll call it a day. These are the notes. Okay, we'll do question 2.4. Like I said, we'll call it a day at that. Okay, so 2.4. Vibrating system, mass 10 kilograms, stiffness 2,500 newtons per meter, damping of 45 newton seconds per meter, harmonic force amplitude of 180 newtons, a frequency of 2.5 hertz, acts on the mass. Find the complete solution. So it says find the complete solution representing the motion of the mass as time goes off to infinity, so the steady state solution. So I've got a few things to do. Let's do this. Driving frequency, okay. We've got omega is 2 pi times by f. That's 2 pi times by 2.5. That's 2.5. Hertz. That comes out to be 15.70 80 radians per second. Okay. The forcing function we have an amplitude of 180 cosine, and then we've got our driving frequency 15.7080 d. Okay, there's our forcing function. Natural frequency omega naught 2k upon m. Any single degree of freedom system that's 2,500 divided by 10. This comes out to be very close to the driving frequency. Whoops. 8114 radians per second. Okay. Gamma T upon m. That's 45 divided by 10. That's 4.5 seconds to the minus 1. Okay. So it's about working out a bunch of values. Okay. And then we stick them into the equation. So A, F naught divided by m. We have 1 divided by the square root of omega naught squared minus omega squared all squared plus gamma omega squared. Okay, so if we do the sums for this, 180 divided by 10, 1 divided by square root of 15.8114 squared minus 15.7080 squared all squared plus 4.5 times by 15.7080 squared all square rooted. If you do that sum on your calculator, 0.2544 meters. Okay, delta, we just apply the solution, tan to the minus 1, gamma omega divided by omega naught squared minus omega squared. Four point five times 15.7080. We have 15.8114 squared minus 15.7080 squared. Again, do the sums. 1.5247 radians. So the equation x of t that we know follows this format. And so we've got 0.2544 cosine of omega, which is the driving frequency, 15.7080 t minus 1.5247. Okay. So, like I said, for a vibrating system with a bunch of values for the frequency, for the mass, stiffness, and damping, is that being shaken by a system that's oscillating at 2.5 hertz with a force amplitude of 180 newtons. What's the solution of the system in terms of the displacement? And so, like I said, you basically go through the process of finding a bunch of terms, omega, the force amplitude, the natural frequency, and the specific damping, specific damping. You apply them to the equations for A and delta. You apply them to the equation to get your answer, basically. Okay. Okay, so like I said, these solutions are on Blackboard. They'll also be part of this recording of this session. Okay, so you'll be able to see them in multiple places. Let's just go back and see what else I don't think there's anything else in the presentation apart from the example. Let's have a look. Yeah, so there's the example question. It's about a boy riding a bicycle over a curb. What's the response? It's a sort of free damped system problem. And like I said, if you want to go onto Blackboard, you'll be able to find the solutions to that. And then if we go to objectives, we've got after studying chapter 2 of the course notes, you should be able to be familiar with the standard and alternative forms of the solutions to both free and forced, undamped and damped single degree of freedom equations and understand how these have been determined. The alternative forms are actually next week. Okay, so we're going to be doing the same thing but with slightly different equations. And then also understand how for force systems amplitude ratio varies with different drivers. The next week, obviously, you'll be looking at the identifying the correct form. So you're given a problem. I've not given you the sort of which form it's going to be in. Can you identify the correct form? And can you convert solutions from one form to the other using trig identities? That's the other sort of thing that's worthwhile studying. Okay, so thank you very much for attending this session. I appreciate it. We shall meet again next week. In the meantime, you've got your tutorials to go to where you can ask more questions about these sessions to Neil and Adrian. Okay, make use of them. And also, don't forget that there's another test that opened 5 minutes ago. Okay, and you'll have to do that. That must be completed by 7 p.m. next week, and that's on the content that's being covered in the lectures, the pre-recorded lectures that are now available online. If you've got any more questions, then please let me know. In terms of the formula sheet for Mohammed and Garson, the answer is no, because the assessment for this module is open book, so you can take advantage of the book. If you want to use a sheet, then you can make one yourself. There used to be a formula sheet for this module, but like I said, that was when the exam was closed book. Since it's open book, I thought, well, it's a bit generous to give you a formula sheet since you've already got everything in the book. So the answer is no. If you want to make a formula sheet for yourself, then by all means do so. It's possibly quite useful during revision. But hopefully many of the equations that we're going to be using during this module will be used so frequently that you won't need to remember any particular equations. Thank you very much, and I shall see you next week.